Hello, and welcome to the History of the Atomic Theory, where we'll take you through all the exciting contributions and discoveries that helped make the modern understanding of the atom today. This presentation is brought to you by Kelly Cha and Michaela Schwab. Our story begins in 400 BC with a philosopher in ancient Greece. Yes, meaning that he had no science or scientists, and he wore togas. His name was Democritus, and he had the idea that if you took something and cut that something in half enough times, you would eventually reach something that could no longer be cut. He called it the atom, from the Greek word atomos, meaning uncuttable or indivisible. Well, 2,171 years later, in 1772, French scientist Antoine Lavoisier, represented here by this floating head, came up with the idea that in a chemical reaction, the mass of the reactants will equal the mass of the products. He gave us the law of conservation of mass, stating that in a chemical reaction, mass is neither created nor destroyed, only conserved. To prove this, he would take products or chemical compounds and he would break them down into the reactants, massing them at both times to prove that they indeed were equal. Later, in 1803, an English scientist named John Dalton, but bearing a striking resemblance to Harry Potter, proved that the atom was actually indivisible, i.e. the smallest particle that makes up matter. He claimed that the atoms found in one element were identical in both properties and mass, but that they differed from the atoms you would find in another element. He also stated that chemical reactions were simply the rearrangement of atoms in whole number ratios. To top it all off, he created the atomic model known as the billiard ball model. In 1897, J.J. Thomson, the English scientist, took things a little farther when he discovered the electron. To do this, he performed what is known as the cathode ray experiment. A cathode ray is a beam that travels through a vacuum or discharge tube from the negatively charged electrode or cathode at one end to the positively charged electrode at the other end, known as the anode. By testing how these rays reacted to things like heat and magnets, Thomas was able to measure the angle at which they were deflected and calculate the ratio of the electrical charge to the mass of the particles. He discovered that the ratio was the same regardless of type of gas that was used, which led him to conclude that these particles that make up the gases were universal, and it was these particles or electrons that we see in his atomic model, the plum pudding model, appropriately named as it shows negatively charged electrons placed randomly throughout a positive surrounding, just as berries would be in a plum pudding. The next discovery was made a year later in 1898 by Marie Curie, who lived in Paris at the time. She concluded that the amount of radiation depended upon the amount of element present in the compound. Thus, she deduced that radioactivity does not depend on how atoms are arranged, but rather that it originates within the atoms themselves. In the year 1900, German scientist Max Planck created a new theory of energy. He came up with the equation E equals NHF, with E equaling energy, N integer, H constant, and F frequency. In determining this equation, Planck came up with the constant H, now known as Planck's constant. This is said to have revolutionized physics and opened the way for Albert Einstein's theory of relativity. Planck is also credited with the origination of the quantum theory of energy because he had to make the assumption that energy was made of individual units or quanta to make this equation. Next, in 1905, is everyone's favorite guy, Albert Einstein. We are personally a fan of him with his tongue sticking out at all times. Einstein's special theory of relativity sought to harmonize the laws of mechanics and the laws of the electromagnetic field, and based on this theory, he proposed a theory of gravitation. And eventually, in 1916, he published his paper on the general theory of relativity. Can't forget his concept of mass-energy equivalence, expressed by the famous equation E equals mc squared. In 1908, an American scientist named Robert Millikan found an accurate determination of the charge carried by an electron by using what is called the falling drop method. The quantity he found was a constant for all electrons, which demonstrated the atomic structure of electricity. He began a series of experiments to determine the electric charge carried by a single electron by measuring the course of charged water droplets in an electric field. But ultimately, the results were not accurate enough to be convincing. To solve this problem, he switched out water to something that wouldn't evaporate as quickly, oil. And with this famous oil drop experiment, he was able to determine the charge of an electron. Next, in 1911, Ernest Rutherford, an English scientist, discovered the atomic nucleus with positively charged protons and all. He created the nuclear model of the atom, which includes a dense positively charged nucleus containing positively charged protons, and outside the nucleus, moving as if in orbit, are electrons, the number of which he determined was equal to the number of protons. To make this model, he performed what is called Rutherford's gold foil experiment. It involved alpha particles, positively charged tiny particles, being shot at a thin piece of gold foil. In accordance with the Thomson-Plunn pudding model of the atom is just supposed to be made of a lot of empty space and negatively charged electrons. So the particles were expected to pass through the foil with little alteration to their course. And most particles did behave this way. However, some rebounded, and at sharp angles, suggesting that there was a dense and positively charged area in the center of an atom. In 1913, Niels Bohr takes the stage. He's an English scientist who created the planetary model for the hydrogen atom. In his model, the electrons move around the nucleus in fixed orbits like planets do around the sun. An electron in a particular orbit has a constant energy, and an excited electron is an electron that absorbs energy and moves to a higher energy orbit of a larger radius. An excited electron can also fall back to its original orbit by emitting energy as radiation. This is known as the ground state, as it is the lowest energy state of the electron. To construct this model, Bohr used something called the emission spectra of hydrogen, a collection of different series using ultraviolet, visible, or infrared light to make observations of excited electrons falling back to lower energy levels in a hydrogen atom. The next discovery happened in 1924 when a French scientist named Louis de Broglie formulated the de Broglie hypothesis, claiming that all matter, not just light, had a wave-like nature. This hypothesis was soon confirmed with the observation that electrons, which are matter, also display diffraction patterns, which is intuitively a wave property. This led to the theory of particle-wave duality, stating that matter had both properties of particles and waves, and also neither. De Broglie's ideas were the basis for developing the waves mechanic theory, and he even created a model that described Bohr's model, updated with his understanding of particle-wave duality. 2 years later, in the year 1926, Australian scientist Erwin Schrödinger used math, probability, a wave equation, and Werner Heisenberg to develop the electron cloud model, also known as the quantum mechanical model. It depicts an atom in a sort of cloud, with intensity of color not representing individual electrons, but the probability of finding an electron in any particular position. This directly relates to the discovery of around the same time in 1927 by German scientist Werner Heisenberg, who, as I mentioned before, worked with Schrödinger on developing his model. Heisenberg came up with the uncertainty principle, stating that the measurement of a subatomic particle's velocity and location cannot be made simultaneously. Subatomic particles meaning things like electrons. Instead, scientists would have to use a wave function to predict the location of electrons. Regions where electrons are much more likely to be found are called orbitals, that are of course found and explained by this function, seen in Erwin Schrödinger's model. The final discovery was made in 1932 by English scientist James Chadwick, but you may know him as Jimmy Neutron. Okay, almost, but not really. He inspired Jimmy Neutron's character, as, if you can guess, he discovered the neutron! He claimed that the nucleus of an atom contains neutrons, electrically neutral particles with a mass similar to that of a proton. To find this out, he bombarded beryllium with alpha particles and discovered Rutherford's missing neutral particles, the ones he suggested that made up for the calculated mass deficiency in the atoms that he studied. And there you have it, everything we know about the atomic theory, thanks to the hard work of scientists past. We've come pretty far and we've got a lot farther to go, but for now, that's all, folks.